Astronomers have now identified roughly 10 stars that get torn into by the same supermassive black hole again and again, on repeating orbits, and survive every single pass. 4 of those stars have been doing something that broke every existing model. Each time the black hole rips into them, the resulting flash of light gets dimmer than the last one, with no clear reason why. For years nobody could explain the fading. This year a team of astrophysicists at Syracuse University says they have found the missing piece. And it is not about the black hole at all. It is about how fast the star itself was already spinning before it ever got caught. Today you get what a repeating stellar near-miss actually looks like. Why the dimming flares stumped researchers for so long. The spin-based fix the new study proposes. And the honest limit on how confirmed that fix really is. When a star wanders too close to a supermassive black hole, the black hole's gravity can pull harder on the near side of the star than the far side. A stretching force strong enough to rip the star apart entirely. Astronomers call that a tidal disruption event. And it happens once, because the star is gone afterward. What astronomers have now confirmed in about 10 known systems is a different, rarer version. The star's orbit only grazes close enough to strip off an outer layer of gas each time. Not enough to destroy the core. The wounded star survives, loops back around on its orbit, and gets stripped again on the next close pass. Sometimes years later. Each strip generates a bright flare as the pulled-off material falls toward the black hole and heats up. Researchers call these repeating partial tidal disruption events. And finding even one confirmed case was considered a rare catch. Finding 10, several of them tracked across multiple flares, is what let anyone notice the fading pattern at all. The simplest expectation is that if a star keeps losing roughly similar amounts of material on each pass, the flares should stay roughly similar in brightness, maybe trending down slowly as the star shrinks. That is not what 4 of the tracked systems did. Their flares dimmed noticeably from one pass to the next, in a pattern that did not fit the standard models astronomers use to describe how much gas a black hole strips off a star per orbit. For years this sat as an open puzzle in the repeating disruption literature, with no agreed explanation. Some researchers wondered if the star's structure was changing in some unmodeled way after each hit, or if measurement effects were distorting the picture. Neither explanation held up cleanly against the data. The puzzle mattered because these repeating events are one of the few places astronomers can watch a black hole interact with the same object more than once. So an unexplained pattern in the fading meant a real gap in the physics being used to model it. A team led by doctoral student Ananya Bandopadhyay, alongside postdoctoral researcher Benjamin Amend and associate professor Eric Coughlin at Syracuse University, published a new model in the Astrophysical journal that adds a factor previous versions had left out entirely: how fast the star was spinning before its very first encounter with the black hole. A star that starts out rotating quickly responds differently to the tidal stretching than a slow spinning one, changing both how much material gets peeled away on each pass and how that amount evolves as the star's shape and rotation shift after every hit. Run through the math. A star with high initial spin naturally produces a sequence of flares that start bright and fade over repeated passes, which is exactly the pattern the 4 puzzling systems showed. The same spin factor also helps explain how these stars end up on such tight, repeat-prone orbits around the black hole in the first place. Since fast rotation changes how easily a star gets captured into a close loop rather than flung away or fully destroyed on the first encounter. Nobody has directly measured the spin of any of these stars before they were captured. Spin is not something telescopes can read of a star that is thousands of light years away in. Already mid-disruption, what the Syracuse team did is show that a fast-spinning star fits the observed dimming pattern better than a non-spinning one in their models, which is strong theoretical support, not a direct confirmation. The sample size is also small. About 10 known repeating partial tidal disruption events exist in the entire astronomical record, and only 4 show the dimming pattern the new model was built to explain. That is enough to build and test a hypothesis, but not enough to call the spin explanation settled physics. Other unmodeled factors, such as the exact composition or internal structure of each star, could still be contributing to the fading in ways the current model does not capture. The honest state of things is that this is the best explanation on the table right now, produced by researchers who are explicit that it needs more repeating systems and more data per system before it can move from leading theory to established fact. Recap. Astronomers have confirmed roughly 10 stars that survive repeated close passes with the same supermassive black hole instead of being destroyed outright. And 4 of those systems produce flares that mysteriously dim with each pass. A 2026 study from Syracuse University proposes that the star's spin before its first encounter is the missing variable, and shows that fast-spinning stars naturally produce the fading pattern seen in the data. Signal or noise? Signal on the observation. Promising theory on the explanation. The repeating survivals and the dimming pattern are real, measured, and published across roughly a decade of tracked systems. The spin fix is the most convincing model proposed so far, built by researchers who are upfront that it is inferred from fit, not measured directly, and tested against a sample small enough that 1 or 2 new systems could reshape it. That is what a good new idea in astrophysics usually looks like before it hardens into consensus. Subscribe for the discoveries that separate what was actually observed from what still needs one more round of data. Signal from the noise. Every week,